Our speakers in this afternoon's first session is Murray Close from ESR. So Murray, do you want to come forward? Who's going to talk to us on groundwater research, making the invisible visible. So I think your slides are up there. So welcome to the podium.
Great, thanks. Okay, if we look in terms of what groundwaters are, in terms of globally, if you look at all the unfrozen fresh water, 95% of that is in our groundwater systems. We drink groundwater for our drinking water, over half of us do, in addition to significant agricultural and industrial uses. But I think it remains very understudied because it's very difficult to access. You've got to drill a well, and it's often overlooked because of that difficulty of access. United Nations World Water Day last year had the slogan, groundwater making the invisible visible. So I've taken that as my title for today, this afternoon's speech. And at this stage I'd like to acknowledge the colleagues for the last couple of decades who've contributed to this research. So I'm going to illustrate the making the invisible visible from a couple of places, looking at how understanding the structure of heterogeneous alluvial gravel systems and how can we incorporate that into making better predictions for source protection zones for our drinking waters and understanding the natural ecosystems in our groundwaters. So looking first at the structure of alluvial gravel aquifers, in the last couple of decades we've carried out tracing experiments that have demonstrated the presence of permeable zones or channels that basically can conduct water and contaminants, and particularly microbial contaminants, at 100 to 1,000 times faster than the bulk material in our groundwater systems. So I'm going to look at three questions. What are these structural features? How connected are they? And how can we feed this information into groundwater models that it can actually do a better job of predicting protection zones for drinking water wells? So here's a couple of pictures of the major alpine rivers in the Canterbury Plains, the Waimakariri and the Rakaia River, and they basically have been transporting water and sediment across from the mountains to the sea over the last few thousand years, forming the Canterbury Plains, which is a very productive aquifer, and similar aquifers occur throughout New Zealand. But if you look at what makes it up, if you just dig it up in an auger, it just looks like a mixture of gravel and sand and silt, much like you'd make concrete from. But if you go down and actually have a look at the structure, either through an auger hole or through cuttings or cliff faces, you can see a lot of structure. Whoops. Okay. Oh, right. This is the sandy gravel stuff, which is the bulk of the material, but you've also got lenses of sands, and then over here you've got these open framework gravel lenses. This is coated with iron, and down here you've got one that is non-coated. And over here you've got an insert, and the main feature of these open framework gravels is the lack of fine material. No sand, no silt. And so they're just these coarse gravel particles, and they conduct water and contaminants incredibly rapidly. So we've done a lot of studies of these sort of profiles, and we've got some information together in terms of the structure, the frequency of these different sort of lenses, and generally speaking, they're like long ribbons. They're sort of fairly flat, reasonably wide, but they sort of extend in the direction of deposition for at least 1 kilometre. We've traced bacteria 1 kilometre in the groundwater systems. So how connected are they? We went to a cliff face in South Canterbury. There's a cliff just down there. It's about 10 metres 10 metres deep, we drilled these 9 auger holes. They were 1.2 metre diameter auger holes, so we could go down with some protective steel casing, temporary casing. And in terms of a trace of how connected these things were, we used smoke. And we just used a simple party smoke machine. We used a leaf blower to provide a small positive pressure. And then we sealed up the middle hole in sequence. And this is what it looked like down the middle. We had a pressure sensor, we had a light source so we could see what was going on, and we had the party smoke machine producing smoke. And then, if I can get this thing going, and we went to a hole 5 metres away, and hopefully that'll work. It does, great. And so you can see the smoke pouring out about halfway down the hole. And this is where it was coming out, and it's basically coming out from this open framework lens just here. And we did multiple tests, and we found basically there was a lot of movement in the direction of deposition, which we'd perhaps expect. Not very much movement in the transverse direction, which gives us this average anisotropy sort of factor of about 6. So incorporation into a groundwater flow model, we basically had a 3-dimensional unconfined groundwater model. And we made 200 realisations of material that would both meet the structure information we had and also meet the connectivity metrics. And so for each one of these realisations of this hydraulic conductivity field, we ran groundwater flow transport model, ModFlow, and we put particles. Here's our model here, groundwater flow in this direction, and we had a pumping well here, and we put particles all over this place, and within that zone, we identified particles that would reach the pumping well within a year, which is the time period for microbial transport that you're worried about. And so when you're right close here, 25% of the particles would reach the well, whereas at the outer rings there was 1%. And so this gives a really good picture of a source protection zone that's got some basis in it takes into account the heterogeneous properties of the groundwater system. Okay, looking at the second example, aquifers don't only have water, but they also contain lots of life. They're a complex ecosystem of viruses, bacteria, protozoa, and stygofauna. And there's this web that we can see there, and I'm just going to look, because of time, at the top lot, the stygofauna. They're the top level of the groundwater food web, and they live all their life in a quite unusual environment. It's dark, there's no sunlight there, food and energy are scarce, low oxygen levels are often present, and very stable temperatures. And these tend to be reflecting of that environment. They're colourless, opaque, no eyes. And so up on the upper, the upper left are copepods. They're about 1 millimetre long. Over here are some amphipods. They're about 3 to 5 millimetres long. And at the bottom, you can see a scale bar, which is 2 millimetres. So these are more big organisms, and they're about 15 millimetres long. So they live within the pores of the groundwater system. So the big organisms, you only really tend to find them either in karst environments or alluvial gravel situations. We've got some beautiful videos of these things down some of our wells, but no time for that in 10 minutes. So what do? They help maintain aquifer properties. There's been experiments carried out showing that amphipods can maintain the effective porosity of sediment columns by biotubation, which is basically burrowing and mixing the sediment up. They also graze on the bacteria and the protozoa and keep their abundances down, so that it basically stops or helps prevent clogging of the aquifers, so that they can continue to deliver the water and other services. But in terms of their vulnerabilities, I guess it's reflected because they're adapted to a very stable environment. So they're quite susceptible to small changes in chemistry, quality, seasonal variations. I'll be quick. And so looking at the chemistry, for example, there's been some ecotoxicity studies. And if we look at the picture at the bottom, it shows that the stygofauna tend to be a little bit more sensitive compared to D. magna with respect to insecticides, a bit less sensitive with respect to heavy metals, and a bit of a mixture. So they're not consistently more or less sensitive, but we actually need to do some actual work on those organisms. So in conclusion, groundwater is often out of sight, but it should never be out of mind. Understanding the structure of our heterogeneous groundwater systems can provide better protection for our drinking water wells, and that is an important and fascinating ecosystem under our feet that we're just starting to explore and understand. Thanks.
Thank you very much indeed, Murray. It's fascinating to see the innovation of research methods and tools, hardened smoke machines and a leaf blower.
Yeah, totally. Yeah.
Wonderful, that innovation. So, are there questions, Murray, on groundwater, its visibility, invisibility? Karen?
Yeah. So hydraulic conductivity measured with air, is it the same as for water? So when you measure it like that, you can use it in a water model?
It's relative, yeah. I mean, we did it in the unsaturated zone where it was air and smoke, but the same structure continues down for hundreds of metres actually in terms of the thickness of the gravel, and so we were using it as an analogue basically here. Yeah. Yeah, it only took less than a minute to travel the 5 metres, so it was incredibly connected. Yeah.
What sort of events cause, a long strip of gravel and non-infilling to, what happened? Why was that laid down like that?
Yeah, that's a really good question. I'm not a sedimentologist, but it's basically to do with as the rivers, they form bars and I guess coarser layers basically, and they sort of progress as the river waves around. I'm not a sedimentologist, but it's that sort of thing.
The whole of the Canadian Plains has been rivers at different times.
Exactly, yeah. And basically the rivers, as the sediment comes into this bit, they flood and go over there, but and they sort of swing round, yeah. Brent?
Do you do anything on artesian systems and sort of connectedness from what was sort of free water becoming artesian, and looking at how the artesian system works?
Not particularly. We've tended to do most of our work in the shallow, unconfined systems because they tend to be, the artesian systems have got a lot of protection, and their recharge areas are often a long way up gradient, so they tend to be better protected than the shallow, unconfined, so we've focused more on that, yeah. Yep. We've done a lot of work on nitrates in the last 15 years, I guess, at least. And certainly for the Canterbury gravels or Canterbury plains, but in a lot of other places as well, if you've got a lot of oxygen in your system, nitrates tend to persist, and so they'll basically just keep going through the groundwater system into the shallow streams and lakes and those sort of things. So some of our research has been, can we actually intercept that nitrate and denitrify it basically, yeah. Yes, you can, and we've demonstrated it on a pilot scale, but because it's such a diffuse contaminant, you can do it in small areas, and so you've basically got to find zones where you've got converging flow lines, so you've got a lot of the groundwater coming into an area, say like a gorge, you know, where the groundwater comes into a point, and then if you built something there, you could intercept quite a bit. Yeah.
Otherwise, it's ineffective apart from a highly localised.
Yeah, and it has certainly been used a lot, for example, in the States as an edge of field mitigation, so that whatever you do on this particular field doesn't go down gradient, and so there's possibilities for that, yeah.
Right, well, thank you very much,
Cool.
Murray.
Thank you.
Thanks very much.